Okay, so the first thing I want to mention today is there was one problem that we had on the quiz. I haven't finished all of them because so many of them came in after midnight last night. The first question on the quiz, it is, we have a function g of x equals x cubed minus 3x plus 6, and you're asked, does this satisfy the hypothesis of the mean value theorem? And if it does, then the conclusion would be guaranteed. Now, every single person attacked this the same way. They took the derivative, they found the slope of the secant line, set it equal to the slope of the tangent line, solved, did all that good work. But not one person so far has addressed the first thing was, does it satisfy the hypothesis? Because if it doesn't satisfy the hypothesis, there's nothing to do in the rest of the problem. So remember, the hypothesis is that your function is differentiable over the open interval and the endpoints exist. And nobody's addressed that. So I want to make sure we understand that that's that's actually the most important part of the entire answer, because if that's not satisfied, there is no conclusion. The conclusion was you came up with c equals the square root of 13. Most everyone got that. That's the conclusion. The hypothesis, so this is a polynomial. And we talked about this before. Polynomials are continuous everywhere, and more importantly, they are differentiable everywhere. Continuous is where the function is defined. So because the domain is all real numbers, that means this is going to be continuous for all real numbers. Okay, if you're defined for all real numbers, you can't have a discontinuity in this situation unless it was a piecewise function, and we're not doing any more of those. Secondly, can I take the derivative and evaluate it at every place in the domain? Yes, I can. If I'd had a quotient, if I have a denominator here, then maybe I can't. But in this case, polynomials are wonderful. So the first step in this problem would be to say something of the fact this function is differentiable over the whole number line, therefore it's differentiable over this interval 2 to 5, and therefore it's also over the closed interval. And then we go on and proceed from the problem. Now, the rest of the quiz was pretty good. Most of you did a really nice job in finding your derivatives, setting them equal to 0, finding your intervals. There's only a couple of common errors. One of them, and again, I will repeat this every time, because funny thing about Calc 1, I find students come up with their own way to do every single thing in math from now on the rest of their lives. And your own way usually is not the right way. There is only one accepted path in 99.97% of all the math you'll do the rest of your life. Occasionally there's 2 paths, usually there's 1. So if we're trying to find extrema are y values. Your input would be critical numbers. So when I get people saying x equals 3 is the absolute max, that has no meaning mathematically. You picked a point on a number line and said it's the highest value. That makes no sense. F of 3 being the highest value makes sense. X equal 3 makes no sense. No, that's an x value. That's the input. That's the critical number. Extrema are y values, period. There's no exception to that, and there's no interpretation necessary. It's the definition of the word extrema. Extrema refers to whether it's a maximum or a minimum. So that's why we use that word, because you might have a maximum, you might have a minimum, you might have both, you might have neither. You might have multiples. Okay. And the other thing is, just want to make sure everybody's on the same page, is the intervals of increasing and decreasing sometimes give us some issues. Like, how do we do this? So I showed you a really simple way to sketch a picture, and what I'm seeing on the quizzes is most of you are doing a great job of sketching the picture and then interpreting the picture correctly. But intervals of increasing and decreasing have to be open. There is no such thing as a closed interval when discussing continuity, differentiability, increasing and decreasing. Intervals have to be open. And so sometimes I see closed intervals as answers. That's actually 100% incorrect. Okay, and here's what I mean. If we said that we have a critical number, let's just say hypothetically, x equals 5 is a critical number. So you have, it's increasing from 5 to infinity, and you have it's decreasing from negative infinity to 5. We have some contradictions here. You're increasing where the derivative is positive. You are decreasing where the derivative is negative. So right off the bat, you're saying the derivative is positive at 5, and at the same time, the derivative is negative at 5. Oh, but you also said the derivative was 0 at 5. That means in simple English, you just said the number 0 is both positive and negative simultaneously, which is not true. It's not even a little bit true. No, 0 is neither positive nor negative, which is why both of these would have to be open. It's a contradiction, really big contradiction, if you try to say you have a closed interval in that case. So we want to make sure that didn't happen very often, but it does show up. And, you know, every now and then. So today it's all about graphing like we did last day, but now we're going to talk about a different part of the graphing. So here's the example I love to use. Okay, I can't do it in front of you. I usually do this in the classroom. I will start at one end of the room and I will actually do this. And I'm going to run across the room as fast as I can. Well, I don't want to pull a hamstring, but I'll run pretty fast. And I'm going to run to the other side of the room, but you know, I got to slow down before I hit the wall. And then I'm going to turn around and run the other way. And I'm going to do this a couple times. So when you're looking at me going back and forth, I am not running at a constant speed. I can't, because I have to stop at both ends. So obviously I'm speeding up, and probably somewhere in the middle, I've hit my maximum speed, but then I got to slow down. And then I get to the other side, I start speeding up going backwards. So if we consider this direction to be the positive direction, like a number line, then when I'm running this way, my speed should be a positive number. But when I'm running the other way, it should be negative. Remember, velocity, the concept of velocity, it has to do with vectors and things, but positive and negative because there's direction. So in this direction, if it's positive and I'm going in this direction, then we'll call it negative. So like the slope of a curve, if my curve is going uphill, we'd say the derivative is positive. If my curve is going downhill, we'd say it's negative. And in that case, that would correspond with speed. So I'm running, but then I'm slowing down. I'm coming to a complete stop, and then I'm starting to go the other way. Now, if you were driving a car, and you put your foot down, you'd be speeding up. And as you take your foot off, you'd start slowing down, and then you put your foot on the brake, maybe you necessarily are going to stop. That thing that you put your foot on, does anybody know what that's actually called? I have fun with this one because most people don't. You do, but you forgot. What are you putting your foot on?
The accelerator pedal.
It's called the accelerator. We generically call it a gas pedal. No, it's called an accelerator. That's the formal name of that thing you put your foot on to get gas, meaning you are accelerating. So we're going to talk about acceleration because that's actually considered more important mathematically than speed. Oh, so acceleration would mean I'm speeding up. But if I'm slowing down, we usually call that deceleration, which is the same meaning as negative acceleration. So, excuse me. So let's talk about, I've got distance and time. So this is time. This will be distance. We always use S. S has to do with arc length and distance and things like that. Don't ask me why. This is just typical. So I'm starting from a dead stop. I'm speeding up, I'm going, and I'm slowing down. And maybe here I got a dead stop. Now I used this picture the other day when we were talking about the mean value theorem. And I said, let's draw the, from here to here, and that secant will be the average speed. That's true. The slope of the secant would be average speed. Now, we all agree that I'm speeding up, I'm speeding up, I'm speeding up, and now I'm slowing down, I'm slowing down, I'm slowing down. So as I increase, remember, acceleration basically is speed per time. So if the units of speed are distance per time, okay, then the units for acceleration are distance per time squared, distance per time per time. Oh, okay, so we say things like, the acceleration due to gravity, right, is roughly negative 32 feet per second squared, or roughly negative 9.8 meters per second squared. We know that. That means if I'm free falling and I haven't gotten so fast that I have to worry about terminal velocity and air resistance and all those kind of things, I'm falling in a vacuum, then every second I'm going to speed up 32 feet per second, every second. Or I'm going to speed up 9.8 meters per second every second as I'm falling. That's what it means. So when I'm looking at my curve, clearly I'm going faster, 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 and somewhere I'm going slower and slower and slower. So somewhere in here, something's happening here. My speed is positive the whole way. At all times, my speed is positive. There's no question. So ds dt, which would speed, and even in Calc 3, ds dt means speed. That's the universal translator. This is clearly positive. I'm always going up until the moment I stop, it's positive. Now, the second derivative, what would the second derivative be? Well, if the instantaneous rate of change of distance per time is called speed, then the instant rate of change of speed per time, this is acceleration. oops, sorry, 1L, acceleration. So acceleration is positive, but here I'm slowing down. So here, acceleration would have to be negative. In this section here, I'm still speeding up. So the question is, what's happening right here? Now, remember I said I'm running across the room back and forth. I am going faster and faster and faster. And somewhere in the middle, I have to start slowing down or I'm going to run through the wall. And that would be bad because, you know, have a hole in the wall or I break, one or the other. So somewhere in the middle, I've reached my maximum speed and now I got to start slowing down. Okay, so my speed reached its maximum right in the middle, but I stopped speeding up and I'm getting ready to start slowing down. So right at that moment, my acceleration is actually 0. That's the moment, right then you took your foot off the gas just for a brief moment. And now I'm starting to slow down. So at this place right here, my second derivative would be 0. My acceleration is 0 because the rest of the way before I hit the wall, my acceleration is actually negative. I'm decelerating. I am slowing down. My rate of change of speed per time is now negative because I'm going slower and slower and slower and eventually stopping. So we're going to talk about this in terms of graphing and other things. That point right there, we have a name for it. It is called an inflection point. Now, another way of thinking about this, and we do study this in great detail in Calc 3, is I call it the windy road problem. So imagine you're driving on a windy road. You're driving to Borrego Springs, right? And that's just crazy windy roads. So you're driving, you know, here's your windy road. So as I'm driving, my steering wheel is cranked hard to the left, and then over here it's cranked hard to the right and then hard to the left. Well, when I'm doing that, doesn't there have to be a brief moment in time when I'm cranking my steering wheel hard to the left? Well, if I never change, I'm just going to drive in a circle, obviously. Oh, but at some point now I'm going to crank it hard to the right. And then at some point I'm going to change it back to hard to the left. And then at some point, you notice it really at that brief moment right there, or that brief moment right there, that's when my steering wheel is just set. I went hard to the left and now I'm hard to the right. There's a moment when my steering wheel is just right in front of me. It's not moving left or right. It's when I change the bend in the curve to bending the other way, that would be called an inflection point. Okay, so anytime you have a windy road, you have these places where your steering wheel is going to be just straight for just a moment before you start cranking it the other way. So mathematically, that has to do with the second derivative, and very specifically the second derivative equaling 0. So now let's go to another graph. I keep knocking my eraser off the board here. Again, I want you to have a mental feel for what's going on. So let's consider I have a picture, you know, keep it really simple. I have a graph, and my graph basically is, you know, it's doing something like that. It doesn't have to be a polynomial. It's doing something like that. Now we know the first derivative, well, let's say that's the peak and valley. All right, this is y equal f of x. We already know in this region right here, f prime of x is positive. We know in this region right here, f prime of x is negative. And we know in this region right here, f prime of x is positive. Why? Because the graph's going uphill. All of my tangent lines would have positive slope. All of my tangent lines would have negative slope. All my tangent lines would have positive slope. That's kind of a no-brainer. So what if I draw the graph of the derivative of this? Now, remember when we found the derivative of the sine function, I loosely graphed the derivative in terms of slopes. And you remember we created the cosine function. We could see it right in front of us. If I said, let's consider what is the graph of the derivative. Well, that's actually not going to be that hard. I'll do it in black. You see, at this point right here, the derivative would be 0, wouldn't it? So the derivative would be right here. At this point right here, the derivative would be 0. Now, along here, all my derivatives are positive. So my derivatives should all be above the axis. So probably, you know, something like this. But But you notice my derivatives went from large positive to less positive to less positive to less positive, eventually to zero. So those are my derivatives. They're getting smaller and eventually zero. Now over here, I went from a derivative of zero to my derivatives getting bigger and bigger and bigger and bigger and bigger. So what's happening in between these two? Well, now my derivatives are negative. Oh, my derivatives are negative. Oh, somewhere in here, I don't know, maybe about right there, my derivative is the least it's going to be. You see, I was positive, positive, less, 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 zero, a little bit negative, a little bit negative, bigger negative, bigger negative, bigger negative, less negative, less negative, less negative, zero. So that guy right there, we'll call that C. So another way of thinking about this, and this is a really easy way to think about this. Look at the shape of my graph before the black dot. It looks like this. Look at the shape of my graph on the other side of the black dot. It looks like this. This cup looks like it's opening upwards. This cupping looks like it's going downwards. And that would be an accurate description. Right here, my graph is going bending downwards, and from there on, it's bending upwards. And again, that's called my inflection point. And this right here, F double prime of C will be zero. Okay, that's where the derivative of the derivative is zero. See, if this is my derivative graph, that's where the derivative has a horizontal tangent, which means its derivative is zero. So what's happening in here, in this region, and well, I missed, okay. In this region right here, F double prime of X, I'm bending downwards. It's negative because I went from very steep slope, less, 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 zero, and now we're starting to get negative. Yikes. Now, from this point on, big negative, less negative, zero, little positive, big positive, big positive. In this portion of the graph, the second derivative is therefore positive. So when the graph is bending down, it's because the second derivative is negative. When the graph is bending upwards, it's because the second derivative is positive. Oh, and I changed from a negative second derivative to a positive second derivative right at this point. That's why it's called an inflection point. That's where the graph changes shape, not direction, shape. This isn't a value, this is a place. Okay, extrema are numbers. Critical values or critical numbers are numbers. They are x coordinates. Extrema are numbers. They're y coordinates. This is a place. This is an address on the graph where I can put my finger right there and say the graph completely changes shape right at that point. That's why it's called an inflection point. It's not a value. It's an address. It's a location. Okay. So we're going to continue looking at this kind of stuff. And so I want to point out all graphs other than lines. Lines are the only graphs that do not change bend because there's no bend. So there's a word that it's equivalent to bend. Okay. The word concave literally translates as bend. Now, people confuse this in physics. They use things with lenses. They talk about no, that's completely unrelated and by the way, that's a non-mathematical term. That has nothing to do. The word concave means bend. And there's two ways I can bend. I can bend up, I can bend down. Now, concavity, this is a numerical measure. Of the amount of bend. So if I have an extremely windy road, the concavity would be large. If I'm really barely moving, I'm gradual hills and valleys, the concavity would be a very small number. And if I was on a line, the concavity would be zero. The concavity of a line is zero because there's no bend at all. And there's the number that measures the bend would be zero. So we're going to show that for all lines, the concavity is zero. That's actually very, very easy. So that's what it is. So concavity, I can bend. There's exactly 4 shapes a graph can have if it's not linear at any particular point. The graph can do this. The graph can do this. The graph can do this, or the graph can do this. All graphs are going to be one of these four if they're not aligned. Now, I'm not talking about where the horizontal tangent is. I'm talking about the rest of the graph. So let's identify each of these. In the first two cases, clearly, in both of these, the derivative is positive, isn't it? Because I'm going uphill. In both of these, the derivative is negative because I'm going downhill. But how I'm doing it, this is I'm going uphill and I'm going faster and faster and faster and faster. So this would be like I got my foot on the gas pedal and I'm being launched into space here. So in this case, the second derivative would also be positive. But in this one, yes, I'm going faster. I'm going forward, but I'm slowing down and decelerating. So in this case, my second derivative is negative. Ooh, so this one is bending upwards. This one is bending downwards, quite literally. And the easiest way to think about this, if this was a road, which way are you turning your steering wheel? As you're moving left to right, if this was a road, your steering wheel would be turned to the left. If this was a road, your steering wheel would be turned to the right. And that would always indicate your concavity, whether it's positive or negative, always. Again, the number line moves left to right. So in this case here, I went from really steep negative to less negative to less negative, which means technically I'm actually speeding up. Because think about if it just kept going. Oh, so in this case here, the concavity would be positive. I went from big negatives to smaller negatives. Now, how about here? I went from small negatives to big negatives. I'm speeding up my backwardsness, if you will. So in this case, the concavity would be negative. So if the bend is upwards, like in these two cases, we say the concavity is positive, the numerical measure, or the word we use is we just say it's concave up. In these two cases, we say it's concave down. So whenever you're asked, what is the concavity of your graph? You'd say, oh, in this interval, it's concave up. In this interval, it's concave down. You don't say it's concave because a graph is concave for the entire domain if it's not aligned. So my graph bends. Well, yeah, that's nice, but which way does it bend, up or down? That's what we're measuring here. So this always would be the second derivative. So what we're going to do is we're going to do a few graphs and some that we've already done, and we're going to measure more about the graph, because with the second derivative, you can complete the picture. You can say everything there is to know about the graph. I'll give you a simple example. You've just got done plotting a few points on your graph, and you figured out, maybe that was a high and that was a low, and okay, here's my graph, and maybe I'm going to put a little arrow here and a little arrow here. That's great. And you might be right, but is this going this way or is this going this way? Is this going like this or is this going like this? In other words, am I speeding up or am I slowing down? I don't know. That would require the second derivative. That can't be found by plotting points, unless you're willing to plot a lot of points. So we'll start simple. I made a few different graphs. Let's see if I wrote them down somewhere. All right. So the first one we're going to look at is x cubed plus 3. Okay, let's look at this guy right here. Well, clearly the domain is all real numbers. That's nice. I like that. I'm a big fan of all real numbers because then there's no restrictions. When I have square roots or I have denominators, I have logarithms, there's a lot of graphs with restrictions. This isn't one of them. So we want to pick off every piece of information there is to know about this graph, but I want to go to the second derivative right away though. So f prime of x is 3x squared plus 6x minus 9. If I factor this, that would be 3 times x squared minus 2x minus 3, or 3 times x plus 1, x minus 3. If I set that equal to 0, I'll get two solutions, -1 or 3. Great. I have two critical numbers. One of them is x equal -1, one is x equal 3. I know that I will have horizontal tangents at those two values because my derivative is 0. Okay. Now, before we continue, Let's do the second. In other words, before we, the graphing part. This will be 6x plus 6. Huh. And that will equal 0 at x equals -1. So something important is happening. Did I get that wrong? Or hold on a second. Oops, did I just make a boo-boo? Oh, I did make a boo-boo. That should be a plus, shouldn't it? Sorry about that. Hold on. Yeah, I got that backwards. I just caught that. I should have been a plus. So this should be -1 plus 3. So 1 and -3. There we go. Yeah, these shouldn't be the same values. All right. So we have a lot of interesting stuff going on here. Now, I want to go ahead and do my intervals of increasing and decreasing like we usually do. Okay, so let's make a number line. This will be the F prime number line. And I have two values, -3 and +1. Go to the factored form, it's easiest. All right. So I pick a number left of -3, like negative bazillion. That'll be negative, that'll be negative, so I'm positive. Pick a number between -3 and 1, like 0. That'll be negative, that'll be positive, so I'm down here. Pick a number to the right of 1, like bazillion, positive, positive. I'm here, great. I now know, and I'll keep it small. Use the blue one. F is increasing from -infinity to -3, and then again from 1 to infinity. F is decreasing from -3 to 1. Okay, that tells me a lot about my graph. Now over here, we're going to make a number line, and this will be our F double prime number line. And there's only one value on this number line, and it's the number -1. This one's easier. So if I pick a number to the left of -1, like negative bazillion, this is going to be negative. Anything to the right of -1, like positive bazillion. Now, how do I interpret this? Well, this tells me that F is concave up in this interval. F is concave down in this interval. Now, I have extrema, I have inflection points potentially, and I can tell all of that without the benefit of a graph. In fact, you never need a picture to determine any of that stuff. And in fact, picture is inconvenient. I mean, if you don't have a graphing calculator right there, or you have a calculator to plot all your points, that's really inconvenient. I'd like to know, where is the maximum? Where is the minimum? What is the maximum? What is the minimum? Where is the inflection point? Can I get that from this information? Yes, I can. So right now, what do I know here? This graph is going up, it's flat, it's coming down. That means F of -3. What is F of -3? Let's calculate that. F of -3. Oh, actually, I don't need a calculator for that. That's going to be -27 plus 27 plus 27 plus 4. That's 31. Is blank what? Max. I always say blank because we'll figure out absolute versus local. In all of calculus for the rest of your life, there is no process that is simpler, period, than figuring out absolute versus local. Yet, the vast majority of all answers I will ever see will be incorrect because they always turn out to be a guess. Max and min isn't the guess. Absolute versus local is always a guess. And it can't be a guess. It's so easy. It doesn't require anything. It doesn't require even math to determine that. It's absolutely trivial in all problems that exist. And that's even in 3 dimensions. There is no part of the process that should ever challenge you. Yet most people get the wrong answer because they, I don't know what they're looking at. They just, yeah, this is absolute or local, and it will take us about 1 second to figure that out. Now, this is going down, flat, it's going up. So F of 1, which is what? -2, is a blank minimum. Now, how do I know absolute versus local? As x grows without bound, this goes off to infinity. There's no absolute max. As x grows negatively without bound, though, it goes down forever. There's no absolute min. That's it. It's that easy in all problems that exist. Look at the behavior. Is it, as you get extreme, is it going up or is it going down? That's it. Now, over here, this says I am bending up until I get to -1, and then at -1, I start bending down. I change concavity here. The definition of an inflection point is where the graph changes concavity. If I was down followed by down, I didn't change concavity. If I'm up followed by up, just like here, if you were increasing followed by increasing, right, you didn't change direction. I changed concavity here. So what is f of -1? That'd be -1 plus 3, that's 2, 6, 9, that'd be 15. No, hold on a second. So I've got a boo-boo somewhere. Hold on. This should be -1. Sorry. This is 15. So therefore, my inflection point is -1, 15. This is the only time you indicate an ordered pair as an answer. There is no problem that you will ever do in calculus 1 or 2 where you indicate an ordered pair as an answer, except when the question is, where's the inflection point? That's the answer here. That's the answer here. This is the inflection point. Now, I want you to notice something's very interesting about, this is true for all cubics, by the way. This is only true for cubics, no other shape. -3, +1. -1. Huh. +31, -1. Anybody catch that? It's the midpoint. The point, -3, 31, and the point 1, -1, if I take the midpoint, the inflection point. That's true for all cubics. It's a simple mathematical proof, but it's kind of a cool thing. So the inflection point on a cubic is always going to be the average of those two, if there are two critical values. Now, because a cubic can just keep going up, it doesn't actually have to turn around, but it's kind of a cool little thing. Now I'm going to show you one other thing. All of this was first derivative test. We came up with the conclusion of max and min, and we used the first derivative test. Is it possible to come up with max and min and not use the first derivative test? I can't use extreme value theorem because the domain is all real numbers. Turns out there's something called the second derivative test, which is actually significantly easier than the first derivative test. Let me, so I'm going to erase this because I don't need this. And here's the thing. If I take any number in the entire domain and I evaluate the second derivative at that number, it tells me whether the graph is concave up or concave down at that value. Remember, the only time the second derivative is going to be 0 is when I'm using the inflection point. So for every other real number that I could put in here, I'm either going to get a positive or negative value. So the value of the second derivative at any x input tells you whether the graph is bending up or bending down at that point. Okay. So if you knew you had a horizontal tangent and the second derivative, I have a horizontal tangent and the second derivative is negative at where I have a horizontal tangent, that means my graph looks like this. If I have a second derivative that is positive at a point where I have a horizontal tangent, it means my graph looks like this. Again, negative second derivative means I'm bending down. Positive second derivative means I'm bending up. It's actually that simple. So if my second derivative was negative at a horizontal tangent, that means I have a max. If my second derivative is positive at a horizontal tangent, that means I have a minimum. That's interesting. This is called the second derivative test. So let's take -3 and +1 and insert them into our second derivative. I'll use black for that one. So f double prime of -3, f double prime of +1. It's not the value that's so important here. It's the sign of the answer, but we do want the right value. So if I insert a -3 in here, I'll get -18 plus 6, that's -12. If I put a +1 in here, I get 6 plus 6, +12. That's the important part. So therefore, I'm just going to write I'm concave down at my critical number because I got a negative second derivative. That means negative concavity. That means concave down. That means I have a maximum there. Here I'm concave up, so therefore I have a minimum, which absolutely agrees with what the first derivative test said. That's kind of cool. That's kind of cool. So it turns out you can use the second derivative to determine whether you have maxes or mins. Now, the rule of thumb that most people use is real simple. I know how to use the first derivative test because that's the one I learned first. But if my derivatives are getting more complicated, remember the pub problem the other day? I don't think anybody here wants to take a second derivative on that one. If my derivatives are getting more complicated because I have roots or I have a quotient or I have products of functions, then I'm probably going to use the first derivative test to determine my maxes and mins. But if I have a polynomial, we know each derivative is getting simpler than the one before, then second derivative test is always simpler. That's kind of a good rule of thumb. So when asked to find extrema in general, it doesn't matter if you use the first derivative test or second derivative test, you have to get the same conclusion. Now, throw a what if at you. All right. There is one type of problem that is a bit confounding at first. And we're going to look at one like this too. There's a problem that kind of confounds us. Let's consider f of x equals x cubed. Now, there's nothing complicated about x cubed, but this one kind of troubles us, and the three-dimensional version of this one really troubles us. Well, f prime of x is 3x squared, which equals 0 at x equals 0. Aha, I have a critical value at x equals 0. Great. In fact, let's go ahead and analyze this. So there's my f prime, there's my 0. Now, numbers to the left of 0, that's positive. Numbers to the right of 0, that's positive. Well, that's kind of weird. Didn't change direction. What can I say? I can say that f is increasing from negative infinity to 0, and then again from 0 to infinity, and f, I'll just put never, is decreasing. In other words, it's never going downhill. But we kind of knew that. All right, now let's look at the second derivative. F double prime of x is 6x, which equals 0 at also at x equals 0. Oh, that's kind of crazy. I mean, who'd have thunk it? So now to the left of 0, this is always going to be negative. To the right of 0, this is always going to be positive. So f is concave down negative infinity to 0. F is concave up from 0 to infinity. 0 turned out to be a critical number, and it turned out to be part of the inflection point. That's weird. We haven't seen that before, that the same value shows up in both places. Well, we haven't done these before. Now, I'm going to draw the graph. We have a pretty good idea what this looks like. I have a horizontal tangent at the origin. I know that. So is this a max or is that a min? So here's the way it works. So earlier today, Nate and I were hiking up to Everest, and we decided to just climb Everest before class. We had a few minutes extra, and so there was a complete whiteout. I mean, you couldn't see 2 feet in front of me because there's just snow everywhere. And Nate was way ahead of me. So I'm climbing up Everest. I get to this plateau right here, and I'm thinking to myself, "Oh, I've made it to the top. Finally, it's flat." Now, while I'm getting to there, Nate's coming back down from the top. He's coming from infinity, and he gets to here and says, "Oh, finally, base camp." See, from my point of view, I finally reached the peak. From Nate's point of view, he finally reached the valley. Which one of us is correct? Anybody?
Depends on where you're coming from.
Neither.
Both.
Neither. It can't be a high and a low at the same time. Now go back a week. Remember how I defined local max and local min? I said it's possible to come up with an open interval where it's either the biggest or the smallest. But every open interval around here, there's going to be values that are below and values that are above, aren't they? In other words, it didn't go up on both sides, it didn't go down. So that's neither a max nor it's a min. But the derivative was 0, but it didn't change direction. Oh, that's because 0, 0 is the inflection. I'll abbreviate. It's the inflection point. Okay. So it's possible that the same value can produce a 0 for the first derivative and a 0 for the second derivative. It's possible. If that's the case, it turns out it's going to be an inflection point. And I said that's the confounding one. This is neither a peak nor a valley, although at first glance it seems like it should be because we have a horizontal tangent, but I didn't change direction. That's what this told me. Okay, now this says I'm concave down to the left of 0. Well, look at that shape of that graph. Yes, that's definitely concave down. This says I'm concave up to the right. Yes, I'm concave up. I changed the shape of the graph. I changed the bend of the graph. It was bending this way. Now it's bending the other way. So I said, this is the first one and the easiest one, but this one sometimes throws us because we want to give an answer. We all want to say f of 0 is a max or f of 0 is a min, but that tells me it's not. That's why the intervals of increasing and decreasing are so important, because if I don't change direction, it can't be an extrema. All right. Now, let's do some more problems where we have to do derivatives and analysis and such. By the way, I didn't graph the last one. I'll leave that one to you. We are going to graph some of the other ones as they get more complicated, because the graphs themselves tell me a lot, but only after I finish the problem. All right. The next one. G of x equals x to the 4th minus 8x cubed plus 18x squared minus 9. Now, I do want to leave a little room in this case to draw the graph at the end of the problem. And again, when it comes to graphing in general, never draw the graph. Even if you have a graphing calculator, never draw the graph until you're completely done with your analysis for a lot of reasons. One is you want to see, does the graph confirm what you said? But the other thing is you don't know what window to use. The -10 to 10 preset X and Y window on all graphing calculators is usually not going to be the window that you're going to need in the end. See, this is X to the 4th. I'm pretty sure a Y of -10 to 10 isn't going to show me much of the graph because this is going to get really big really fast. All right, so my domain again, all right, my domain, always get used to this. You don't have to tell me that, you got to tell you that. Because if the domain has any restrictions whatsoever, it will affect the final answer. So G prime of x is 4x cubed minus 24x squared plus 36x. Can I factor this? Well, I think I can factor out a 4x. And that leaves me with x squared minus 6x plus 9. Oh, I think I can factor that further. How about 4x times x minus 3 quantity squared? Okay, this will equal 0 at x equals 0 and 3, and I'm going to put the little 2 there. Remember that multiplicity. I have my first derivative is a 3rd degree polynomial, so there should be 3 roots. One of them is repeated, so I really only have 2. So now let's do our different color now. Let's do our G prime number line because I got to leave space here. So there's a 0, there's a 3. And I actually want to write G prime number line because there's going to be a G double prime number line. Now, to the left of 0, negative bazillion minus 3 is negative, but when I square it, it's positive. Okay. Now let's pick a number between 0 and 3, like, I don't know, 1. 4 times 1, that's positive. 1 minus 3 is negative, but when I square it, it's positive. So here, okay. Now let's pick a number bigger than 3. I'd be positive, and I didn't change direction. Again, there's a tendency people would automatically make it alternate. No, things don't alternate. I would say I do a lot of stuff with graphing, and I do alternate, probably close to half the time. Close to half, a little less than half, actually. So if you automatically make things alternate, it means you're going to be wrong most of the time. No, you got to check. Okay, so what does this tell me? This information right here says that G is increasing, I'll abbreviate it, from 0 to 3, and then again from 3 to infinity. It would be incorrect to say 0 to infinity because G prime of 3 is 0. 0 is not a positive number. Okay, you can't include it in the increasing because you're not increasing at 0, you're horizontal for that one place. G is decreasing from negative infinity to 0. That's interesting. So what does that tell me about my graph? It says I was going downhill, I was flat, I was going uphill, I was flat, I was going uphill. It's something like this. I now know roughly that's going to be the shape of my graph. And I haven't plotted a point yet. That's just from this information. Now let's do the second derivative. I don't want to take the derivative of that. I don't want to take the derivative of that. I want to take the derivative of that. A lot of us are not lazy. You factor a derivative so you can find where it equals 0. But if you have to take a second derivative, differentiate the unfactored version. Otherwise, you got to use product rule and stuff. No, that's the first derivative before I factor it. I want to differentiate that. So much easier. So my second derivative is 12x squared minus 48x plus 36. Well, that doesn't look very friendly, but I can factor 12 out of that. And that's x squared minus 4x plus 3. I did that correctly. Oh, but I can factor that. That's x minus 1, x minus 3, and that will equal 0 at x equals 1 or 3. Beautiful. Oh, how nice. It happened again, didn't it? I saw that same number. All right, let me see if I can get this in here. So now I'm going to make my G double prime number line, and there's only two values on that number line, 1 and 3. So going to the factored form, if I pick a number more negative than 1, like negative bazillion, sorry, that should be a 1 and a 3. I'm going to have a negative, and that product is positive. Pick a number between 1 and 3, like 2. 2 minus 1, that's positive. 2 minus 3, that's negative. Pick a number bigger than 3, like positive bazillion, positive, positive, positive. Great. I'm concave up here and here. I'm concave down here. And I will write it, I'll put it over here. G is concave up from negative infinity to 1, and then again from 3 to infinity. G is concave down from 1 to 3. That means I'm going to have 2 inflection points because I changed from concave up to concave down here, and I changed from concave down to concave up here. So I need, what is G of 1 and G of 3? What are those? G of 1, so it'd be 1, so it'd be negative 7 plus 11 minus 1, that'd be 2. All right. And I'll use my calculator for the other one. And then G of 3. Looks like 27. So I have inflection points at 1, 2, and 3, 27. Those are locations on the graph where something really important is happening. Now, finally, what about extrema? I want to know about maxes and mins. Well, I only got 2 critical values, 0 and 3. But I'm not changing direction at 3. Another way of looking at that is the second derivative evaluated at 3 is neither positive nor negative. It's 0. Ooh. Now, if I take the second derivative and I evaluate it at 0, my second derivative evaluated at 0 is 36, which is positive. Okay. That means I'm concave up. That means I have a minimum wherever that is. But over here, I went from decreasing to flat to increasing. So I also know that G of 0, which is what? -9 is the blank minimum. First derivative test tells me it's a minimum. Second derivative test tells me it's a minimum. Now, is it absolute or local? Anybody want to try that one? Because you gotta be able to support that answer. Is this an absolute minimum or a local minimum?
Local minimum because it's infinitely going. So no. So that would be a absolute.
Absolutely.
Absolute minimum because I'm going to infinity in both directions. That's it. Again, if you did anything other than what I just did with my hands, that means you guessed at your conclusion. Because there is no mathematics to arrive at your conclusion other than to say, as x grows without bound, this is going off to positive infinity. As x goes negatively without bound, it's also going to positive infinity. Oh, so any minimum's got to be absolute. Great. That means this graph has a lowest point. Now, can you tell me, I'm going to erase this. Now, at this point, it would be wise to make a table of values if you wanted to draw an accurate graph. What are the kinds of things we need to get on there? Well, we need to get, that kind of stuff. But if I want to draw, if I wanted an accurate graph, I don't really have to go very far in each direction because the most important x values on my graph are going to be 0, 1, and 3. I mean, you do realize that there's not a whole lot of important x values. Now, f of 0, we just said was -9. Now, let's say there's negative. Let's say that's -10. So then 10, 20, 30. Okay. So I am here. Did I get the right place? Yes. Then we said 1, 2, make that be 1 unit, 2 units, 3 units, 4 units. Okay, so 1, 2 there. Remember, your scale in the x direction should never be the same as your scale in the y direction. The y is growing really fast. The x is growing really slowly. All right. We have 327, which is about right there. And I think that's enough. I think I can draw a pretty accurate graph here. I can draw an accurate graph? Yeah. Oh, maybe I'll put one more point. What's f of -1? That'd be 1 plus 8. That's 9 minus 9, 18. Okay, so f of -1 is about here. Okay. That's why I don't need anything else. There's my graph. Lowest point, inflection point. I went from concave up to concave down. Here I had a horizontal tangent and an inflection point. I went back to concave up. That's it. That's my graph. Now, let's go ahead. I want to look at this on a graphing calculator. Let me go ahead and enter this. Since x to the 4th. My light is not that great here. -8 x to the 3rd. Plus 18 x to the 2nd minus 9. Okay, now I want to draw the graph, but if I do the -10 to 10 preset window, that means it's going to go way over here to way over here, but only this high. So all of this will be left out. So instead, my x window, I'm going to go -1 to 4. Why? Because this is going up forever. Well, maybe I'll go -2. I'm going to go -2. Maybe I'll even make it a little bigger. I'll -2 to 5. Okay. So my x window, I'm going to make -2 to 5 because I want to get in everything that's important. My y window, now this is really important. I'm going to go -10 because I want to get that number in there. And maybe I'll go to, I don't know, 40. That's a good enough window. Okay. Oh, shoot, this cut off the top. Hold on. Why did it give, hold on, let me go back to my window again. Oh, that's because hold on, I didn't have, I put 40 in the wrong place. Oops, sorry, let me do that again. There we go. Okay, try that again. I had the 40 in the wrong place. Isn't that beautiful? So I did that much of the graph and you can clearly see that flat spot. And okay, this is where you use the graphing calculator after the fact because this part right here is the most interesting part. It's going flat and then back up again, but it did not turn around. So there's a tendency, if I ask this question, that people will tell me that f of 3 is a maximum or it's a minimum. It's neither. There's an inflection point there because it didn't change direction. Okay, so this is a very powerful graph. Now, we've been graphing polynomials, so let's go to some of the nastier ones. All right, let's look at, I'm going to take the graphs that you did on your previous quiz. You turned in 13 today. So quiz 12. One of the graphs we did on quiz 12 was, or I'm sorry, no, this is the one you turned in today. Never mind. I'm off a quiz. You turned in quiz 13 today. This is from quiz 13. So we just did this problem on the quiz and most people did this well, but I want to look at the second derivative and how it affects my graph. Okay. So probably first thing I want to do is rewrite this. I don't want to use quotient rule. It's a product. So h prime of x is first times derivative of second plus the second times derivative of the first. That would be negative 8x squared plus 8x times e to the negative 2x, which would be, if I factor out the negative 8, x minus 1 e to the negative 2x, this equals 0. Add x equals, oh, sorry, there should be an x here. Add x equals 0 or 1. Okay, most people got that. If I then make my number line, what's happening here? Well, this is always positive, so I can kind of ignore it. If I'm to the left of 0, negative bazillion, I'd be positive, negative bazillion, positive and positive. Okay. If I am between 0 and 1, like a half. Did I get that right? If I am roughly a half, okay, then this guy here is going to be negative, and that's going to be, I said, hold on a second, I just messed that one up. If I'm negative bazillion, sorry, negative bazillion, this is positive, this is negative. There we go. Now, if I'm between 0 and 1, like a half, that's going to be negative, and that's still negative. Okay, now I got it. Now, if I pick a number astronomically large, that's going to be negative, that's going to be positive. There we go. I alternated. So we know that h is increasing. I'll put it here. H is increasing from 0 to 1. H is decreasing, negative infinity to 0, and then again from 1 to infinity. Wow. So this thing's going downhill most of the time. It's only going uphill for a really short period of time. But I do know it's going downhill, flat, and uphill, so there's going to be a minimum here. It's going uphill, flat, downhill, so there's going to be a maximum there. Kind of curious what that graph looks like. Now let's do the second derivative. Now, differentiate it. It doesn't matter which form. It might be easier to differentiate in this form because it's polynomial e. There's going to be no advantage doing it any other way. So let's do it in this form. So that would be first times derivative of the second plus the second times the derivative of the first. Okay. So if I factor out the e to the negative 2x, I'm going to get, don't forget this. So I have 16x, whoops, 16x squared minus 16x minus 16x plus 8 times e to the negative 2x, or 16x squared minus 32x plus 8. And if you want to put it over e to the 2x, it doesn't make any difference because that's a function. So it's neither positive nor negative yet. Now I need to figure out when this is 0. Ooh, well, that's kind of icky. Well, I can factor an 8 out of that, I guess. So I can write this as 8 times 2x squared minus 4x plus 1. That might make it easier, but that's not factorable. Big yikes, that's not factorable. So for me to figure out where this is 0, I got to use my quadratic formula. Okay, so quadratic formula, x equals 4 plus or minus 16 minus 8 all over 4. All right, we all know how to use the quadratic formula. Well, that's root 8. So this is 4 plus or minus 2 root 2 all over 4, or 1 plus or minus root 2 over 2. So I have 2 different places where the concavity may change. Okay, 1 plus root 2 over 2 and 1 minus root 2 over 2. So let's go ahead and make our H double prime number line. Okay, there's 2 values, these. I do not use these. These have nothing to do with second derivative, only these. So 1 minus root 2 over 2, 1 plus root 2 over 2. Now you're going, oh, boy, I don't know how big those numbers are. It doesn't matter. Okay, so if I go extreme to the left, negative bazillion, it's going to be positive. Oops. Now let's go extreme to the right, positive bazillion. I'm trying to make it easy on you here. Now, I need a number, this is going to be the tricky part. I need a number between 1 minus root 2 over 2 and 1 plus root 2 over 2. Well, how about 1? Right? So 2 minus 4 plus 1, that's negative. That's it. I'm done with my analysis for the second derivative. So I'm going to, let's see, I hate erasing anything. Oh, you know, I'm going to erase this. I don't need this anymore. We just did this. This is the limitation of a 3x4 board here. So H double prime is concave up negative infinity to 1 minus root 2 over 2, and then 1 plus root 2 over 2 to infinity. Oh, sorry, that's unreadable. Sorry, like union, how that 1 plus root 2 over 2 to infinity. It's concave down from 1 minus root 2 over 2 to 1 plus root 2 over 2. And because I changed concavity twice, I'm going to have 2 inflection points. One inflection point is going to have this x coordinate, the other inflection point is going to have this x coordinate, and we would just use our calculator to calculate the y values. I'm less concerned with the actual y values. They're going to be very small, by the way, because of that e on the bottom. So lastly, extrema. Okay, when I'm looking at this, decreasing, flat, increasing, I know then that h of 0 is definitely a minimum. Increasing, flat, decreasing, I know h of 1 is definitely a maximum. If I use the second derivative, h double prime of 0, h double prime of 0. Well, if I replace x with a 0, I'd have 1 times 8 over e to the 0, that's just 8. If I replace, what was the other value? 1. 2 minus 4 plus 1, that's negative 1. So this would be negative 8 over e squared. All that matters is that's less than 0. I am concave up here. That means it's a minimum. I decreased, was flat, I went up. That also meant it was a minimum. Here I'm concave down. That means it was a maximum. Here I went up, flat, came down, it's a maximum. So either first or second derivative test tells me what I need to know. And again, most of you on the quiz did a good job with that. Now, determining absolute versus local. Oh boy, I'm running. Let's see. I hate to do this, but let me erase this. You guys can always replay this if you want to find that information. All right. So we know then that h of 0 which is 0, and h of 1, which is 4 over e squared, which is not very big, by the way. That's, what is 4 over e squared? It's less than a half. that's actually, or actually around, I should say it's around a half. This is pretty small. All right. This we just said blank min, and we said this was blank max. Now look at the original function. Can this ever be negative? Look at your function. Can it ever be negative?
No.
No. I have a y value of 0 on a graph that can never be negative. That's absolute. Now, as x grows positively without bound, I'm not sure what's happening, but as x grows negatively without bound, that's growing without bound, and that's growing positively without bound if x is negative. So this is going to definitely go up forever. So this is local. See, as x goes negatively without bound, this is getting infinitely large. This is really small. So that's got to be local. So now the coolest part of all in this problem, what about the graph itself? Now, of course, I would suggest plotting a few points. Let me erase this. To simply get out your x and y, and, or excuse me, make a table of x and y and plot a few points. That would be wise. Nothing below, so there's not really much point in doing much. If that's, let's say that's 1, and that's 2, and that's 3. Okay, 1 minus root 2 over 2. Well, root 2 over 2 is a little more than 0.7. So that would be, around here. So that'd be around here-ish, okay? I said, let's say that's 1 unit, that's 2 units, that's 3 units. Just I want to get some accuracy here. I'd like to know about where these points are, all right? So 4 over e squared, it's about 0.54. So a little more than halfway up. Okay, I know that point's on the graph. I know that point's on the graph. I don't need much more, as it turns out. So let me input this into here, okay? All right, so when I put, where is it? When I put 1 minus root 2 over 2 into this function, I got about 0.25. Not a very big number. Okay, now let's put the other one in. 1 plus root 2 over 2. Oh, you know what? I messed up. I forgot to do the times 2. Oops, sorry. Hold on. 2 plus root 2. I'm going to do that one again. This is about 0.38. It's not very big. About there. Let me do this one again. I messed up. I forgot the 2. Hold on a second. 4 times. I was way off. It's about 0.19. Okay, it's about there. All right, I'm done. Oh, maybe we should put a -1. If I put a -1 in here, then this is going to be 4 times e squared. If I put in a -1, you're going to love this. The y value, if I put in a -1, is almost 30. Something like this. There's our graph. This turns out to be a horizontal asymptote. How do I know that? I know it for several reasons. One is we said the graph is decreasing to the right. We said it's concave down here and concave up here. And this is one of the coolest things you can absolutely know. I have a graph that's decreasing but concave up. and it never touches the x-axis again. That means the x-axis has to be an asymptote. That's cool. So now let me go ahead and draw this on my graphing calculator. Oops, let's go back to the y. Let me clear that last one. So I want to do 4x squared divided by, hold on, where's e? E is always hard to find, it's so small. E raised to the 2x. And 4x squared over e to the 2x. Yes. All right. Now for a window, I only really need to go a little ways, but I'm going to go a little bit further so we can actually see the behavior here. So I'm going to go -1, maybe to 10. And then my y window, I don't need anything. So I'm going to go -1 so I can actually see the x-axis. One of the problems, if you make your, even though this doesn't go below the x-axis, if I make my y starting at 0, you won't actually see the x-axis in your picture. So I'm going to have the y start at -1. So my graph shows it, but I don't need to go very high because everything important happens right in here. So I'm going to say y is going to go from, let's just say -1 to 1. That's enough. Okay. So now, isn't that cool? It's exactly what we just said it was. See, our perfect confirmation. All right, we're going to do one more of something we've already done. So second derivative is cool. And the last one we're going to do is the other problem that you did on the quiz. That was x to the 1/3 x plus 8. Let's call that p of x. Running out of letters here. And again, the domain of this is all real numbers, which is important. I don't want to differentiate in this form. By the way, when I'm plotting points, I definitely want it in a factored form. That makes it so much easier. But when I'm taking derivatives, I don't want it in a factored form because then I have to use product rule. So this is x to the 4/3 plus 8x to the 1/3. So p prime of x is 4/3 x to the 1/3 plus 8/3 x to the -2/3. So that's 4/3 x to the -2/3 times x plus 2, or 4x plus 2 over 3x to the 2/3. This is 0, add x equal -2. It's undefined, add x equals 0. That means something interesting is happening at x equals 0, but it is not a horizontal tangent. Now, what about p double prime? Because most everybody was fine at that point. I want to differentiate it in this form, not the factored form. And then I'll get 4/9 x to the -2/3 minus 16/9 x to the -5/3. So right now I can factor out a 4/9 x to the -5/3. And again, these differ by exactly 1. So I'll be left with that, which is 4 times x minus 4 over 9x to the 5/3. This will be 0, add x equal 4. And this will be undefined, add x equal 0. So at x equals 0, something crazy is happening for both the first and the second derivative. Now, I'm definitely going to change sign at 4. So I suspect I'm going to have an inflection point there. So let's do our second derivative number line, because you guys already have, everybody did this one pretty much well on the quiz already. So I have 0 and 4, and this is the p double prime number line. Okay, so I have 0 and 4, and so because of that fractional exponent, that can give me some issues. So we've got to be really careful here. When I'm to the left of 0, I have a negative number. That 5/3 is important. If I have a negative input, then this is negative, but a negative number to the 5/3 power is still negative. So that's positive. If I pick a number between 0 and 4, like 2, 2 minus 4 is still negative, but 2 to the 5/3, that's positive. And finally, if I pick a big positive number, I'm positive, positive. So I am concave up in this interval and this interval. I am concave down in this interval. So P is concave up from negative infinity to 0, and then again from 4 to infinity. P is concave down from 0 to 4, and that also means I have 2 inflection points. I'll write them up here. All right, so first of all, what is P of 0? P of 0 is 0. Beautiful. P of 4, cube root of 4 times 12. Okay, when I actually plot points, then I will calculate that as a decimal value, but until then, there's no reason to. So that means my inflection points, I'll call them my IPs, if you will, are 0, 0, and 4, 12 cube root of 4. And that's going to be a fairly large number. So this graph here has 2 different places where it changes concavity. Now, here's the most interesting part of this graph is probably not the horizontal tangent, but the evil one. So what we knew, let me erase so I can figure, get rid of this stuff in here. Okay, on the quiz, most of you did a good job in your number line, which was, let's see, for this one here, you had it increasing. So I was decreasing, I was flat, I was increasing, something happened and I continued to be increasing. I did not change direction at 0, but I clearly have an inflection point of 0. How could that be? How could it be that I'm decreasing? So without even plotting points, I can say that the shape of the graph, without plotting points, we'll do the graph in a moment. I say it's coming down, it's flat. Now I'm going back up. I'm going to have a vertical tangent at x equals 0. How do I know that? Because it didn't turn around. It was concave up on the left, and it was concave down on the right. Ooh. So I know the graph is going to have this basic shape. And that's without plotting a single point. That's only using the derivative information. So then once again, this is why I'm so happy I have my titanium here. So what do we got? We've got x to the 1/3. All right. X plus 8. X to the 1/3 x plus 8. Okay, great. Now my window. In this case here, all the interesting x stuff, and I want the x-intercept here, so I'm going to go maybe -10 in the x direction because I would like to see where it crosses the axis. So I'm going to go with -10, and in the I'll just I'll go -10 to 10 in both directions. And my y window. Now, is this ever negative? Yes, it is. This is negative between 0 and -8. Okay, so let's go down a little bit. Maybe I'll just go -10 to 10 in all directions. So I don't exactly know what it looks like. I have an idea. Okay, so let's see what the graph looks like. Oh, you see it? You see it? At the origin, see how we're straight up and down? So it's right there. That's so cool. And I love it. My graphing calculator confirms that I did everything right at that point. Okay, so this is the stuff we've already looked at. Now, the last part, and not the most critical, but maybe the most interesting part of graphing is, what about asymptotes? We know asymptotes can rear their ugly head. Well, it turns out to talk about asymptotic means one graph is looking like another graph. An asymptote is a physical line. And it turns out there are 3 types of lines that you can get. We all know about the verticals. Those are the evil ones. We also know about the horizontals. Those are nice and friendly. But there's a third one called oblique or slant asymptote. And you learned this way back when you were in high school algebra doing hyperbolas. Okay, I'm going to remind you of something you have seen, but maybe never explained why. So let's take a really simple graph like this. I have x squared over a squared minus y squared over b squared equals 1. This is the graph of a horizontally opening hyperbola. That's that guy. Now, you graphed these probably in high school algebra, maybe in a pre-calculus class, and you just mindlessly did something because that you were told this is what you're supposed to do, but you didn't know why you were doing that thing. I would like to solve for y, and I'm going to show you, because the oblique asymptote is the most interesting one we're going to look at, and I want to know how to find it. So if I solve for y, then I would have y squared over b squared equals x squared over a squared minus 1. I want to rewrite this as, I want to factor out actually the x squared over a squared and write it as 1 minus, so if I wrote that correctly, 1 minus a squared. Did I write that? Hold on. Just make sure I didn't mess that up. Minus 1. Yes. Except hold on. Do I want to write it minus 1? Hang on, let me rewrite that in a moment. I want to factor out. Actually, let me write it like this first. I'm going to write it as 1 quotient. This will be easier for you to absorb if I write it this way. Okay, so now what I want to do is I want to factor out from this quantity here, or actually not yet. I want to write y squared equals. So y squared is now b squared over a squared. I'll write it like that. That's actually a cleaner way for me to write it. Okay, now what I want to do is factor out the x squared. I was going too fast, I know. And that would be now 1 minus a squared over x squared. There we go. Okay, y squared is equal to this quantity right here. Now, I didn't say y was equal to, because y squared, think like a circle. A circle is not a function, so you can never write y equals. You can write y equals plus or minus, top half, bottom half. I've got y squared equals all of this. So if I wrote y equals, well, then it would be plus or minus the square root of all this. But the square root of a product is the product of the roots, and these are both perfect squares. So I can actually pull those out in front. That would come out as an absolute value. And this is what I'm left with. Now, we've used this term before. As x gets bigger and bigger and bigger, the role of this term is going to be less and less and less. I've used the term before. It's called a transient term. Okay, that means as x gets bigger and bigger and bigger, by the time I get to x equal 10 or 50 or 100 or 1,000, this is going to be microscopic. So in other words, this quantity here is getting closer and closer and closer to 1, which means the graph is getting closer and closer to just this. Well, if I put an absolute value here and I have a plus or minus in front, then I can actually drop the absolute value, and I can just write this as plus or minus b over a times x. Now, if you wanted to graph a hyperbola on your graphing calculator, this is how you do it. You'd say, do the top half, positive square root, and a second function, do the bottom half, and you would have the perfect hyperbola. But that's not the point. Since this is a transient term and it's approaching 1, that means we can say that my hyperbola is asymptotic. That's what the squiggly lines mean. We've used this before. It's asymptotic to plus or minus b over a times x, because this part here, as x gets bigger and bigger, becomes less and less of a contributor. So if I said, just for example, replace x with a large value, whatever negative b over a times x and b over a times this, it's going to be almost identical values on your calculator. So why is that important? Well, here's what we know about hyperbolas. And I'm not studying hyperbolas in this class. I'm using them as an example to demonstrate the thing we want to know right now. I want to graph this with a little bit of accuracy. Well, I do know if x is plus or minus a, then y is 0. I know these 2 points are on my graph. A comma 0. Now, what is this? That's a line past, those are 2 lines that are passing through the origin. Let's just say hypothetically, let's say that's 0b. Doesn't matter how big b is. Let's just say that's 0b and that's 0 negative b. So that means that the line with slope b over a means up b over a means the line is going to pass through that point. And then the negative would be right here and right here. And I've drawn a graph more accurate than the best graphing calculator on planet Earth can do, and I didn't plot any points. This is how you graph a hyperbola. This is what you learned. But you mindlessly drew these crisscrossing lines having no idea why or where they came from. Now you know, oh, they're actually asymptotes that came directly from the equation of the curve, but they're not vertical or horizontal. They're called oblique, or more familiar terms, we call them slant asymptotes. They are lines, but they're not vertical or horizontal. Every hyperbola is going to have slant asymptotes. And all you need to draw an accurate hyperbola is find the asymptotes, because then your graph's just going to approach it. So hopefully that explains a little bit about what you did way back when. It's not the hyperbola, it's the slant asymptotes that I wanted you to understand. So how does that affect us? How do we know when we have slant asymptotes? Well, actually, the most common case is when I have a rational function. A rational function, of course, is a quotient of polynomials. So let's consider, hold on, I wrote it down. Let's consider g of x is 4x squared plus 8x plus 16 over x plus 2. I want to draw the graph of this. Now, there's a basic rule that governs in all calculus and algebra and so on, that whenever you have a quotient of polynomials, you cannot proceed. You don't take a derivative, you don't do anything unless the degree of the numerator is smaller than the degree of the denominator. That's an absolute rule that's never changed. Right now, my numerator is of a greater degree. Oh, that means before I do anything, including taking a derivative, I should do the long or synthetic division. Okay, so I'll do that first. So my root is -2, and synthetic, remember, you write the coefficients in descending order. Doing long division is fine, but synthetic's faster. So remember, I bring this down and multiply. Hold on a second, did I do this correctly? Hang on one moment. I think I did this correctly. Okay. That's going to be -8, and then that's 0. 2 times 0 is 0, and that's 16. Oh, this one works out very nice. That means that's the remainder, the constant, the linear term. So this is going to equal 4x plus 16 over x plus 2. It is equal to that. Now, do I have a vertical asymptote in this problem? Can anybody tell me, do I have a vertical asymptote? When do you have vertical asymptotes again? Do you remember? Vertical asymptotes anywhere where the denominator is 0 and the numerator isn't. So do I have a vertical asymptote here?
-2.
Yeah, I have a vertical asymptote, x equals -2, whether I did this or this. Oh, okay. That means my domain is all real numbers except -2. Maybe I should say that, don't you think? My domain is -infinity to -2, and then again from 2 to infinity. So I have a graph that covers the entire xy plane except x equal 2 is a vertical asymptote. Again, we did this at the beginning of the course. A vertical asymptote happens when when the denominator is 0, but the numerator is not. Remember, if numerator and denominator are both tending to 0, that means it's a removable discontinuity. That's not removable, right? So when I write it in this form, it's more obvious. So I clearly have a vertical asymptote x equal -2. We will keep that in mind. Now I want to take the derivative. But when I take the derivative, I don't want to take the derivative in this form. I want to take the derivative in this form. Much easier. The derivative of 4x is just 4, and the derivative of this is just -16 over x plus 2 quantity squared. You can think of that as 16 times x plus 2 to the negative first, or you can remember I showed you a rule that when you differentiate a reciprocal, it's f prime over f squared. Now, I want this to equal 0. So if this is 0, then 4 equals 16 over x plus 2 quantity squared. So if I do a little maintenance here, that would mean x plus 2 quantity squared must equal 4. 16 over 4. So x plus 2 must equal plus or minus the square root of 4, or plus or minus 2. And then finally, x is going to be add -2 to both sides. And by the way, you have to add it in front, not after the plus or minus. If I put the -2 on the other side, I will get a wrong answer. It's got to be in front. So -2 plus 2, that's 0. -2 minus 2, that's -4. Aha, I have two critical values. Quick check. If I put a 0 in here, then that would be 2 squared or 4. So I'd have 4 minus 16 over 4. Put a -4 in here. -4 plus 2 is -2, but the square of -2 is also 4. 4 minus 16 over 4. Great. Quick check. Both of these give me a derivative of 0. Awesome. So now let's do our G prime number line. I have -4, I have 0. By the way, should any other values make it to my G prime number line? Wink, wink, nudge, nudge, hint, hint. Should anything else make it to my number line?
-2.
Yeah. Why -2? Because my quotient can change signs at -2. No, my quotient's it's not 0 at -2. It's undefined at -2, but I can change signs there. That's why I have to consider it. Plus, when I make my intervals, there cannot be an interval from -4 to 0. I'm not defined at -2. So I've actually broken the number line into 3 intervals. So let's figure it out. So pick a number more negative than -4, like how about -bazillion? Well, -bazillion, that means this denominator is going to be microscopic and this is going to be hugely negative. So I am here. Did I just do that right? If I hold on a second. If I make sure I wrote that correct. Oh, I'm sorry. You know what? My bad. I'm looking at, that's the function. I want to look at the derivative. Sorry about that. Let's try that again. If x is -bazillion, then this is microscopic and I have 4 minus microscopic. That's positive. Okay. Let's make it easy on ourselves. Now let's go to positive bazillion. Again, microscopic, 4 minus. Now let's pick a value really close to -2. Let's pick a negative number that's really close to -2. That means this quantity is going to be really close to 0, which means 16 over that quantity is going to be astronomically large with a negative in front of it. And that's on both sides. Or you just say, let me pick -3, then I'd have 4 minus 16. If I picked -1, then I have 4 minus 16. I can do that too. So this one's really interesting. Okay, very, very interesting thing going on here. So we can say that G is increasing where? From -infinity to -4, and then again from 0 to infinity. G is decreasing from -4 to -2, and then again from -2 to 0. I have to break this up into 2 intervals because I'm not defined at -2. I can't make that one big interval. So clearly, I'm going up, I'm flat, I'm coming down. I think it's safe to say that G of -4, we'll figure it out in a moment, is definitely a max. Everybody agree with that? Piece of cake. And G of 0 That's got to be a min. We'll figure out what it is in a moment. Just want to get that out of the way. Piece of cake. All right. Now let's do the second derivative. Well, if I think of this as x plus 2 to the negative 2, then the second derivative is going to be positive 32 over x plus 2 to the third. Now, do you notice something? That will never be 0, will it? It's never going to be 0. So that means I'm done? No, because it's still going to be undefined there. So I still need to do my g double prime, and I have the one value on the axis, because I will change concavity. If I pick a extremely big negative value, negative plus 2 is negative, negative cubed is still negative, so 32 over that would be negative. Now pick an extremely positive value, 32 over positive number. Okay. Now there is no g of negative 2. No. There's no inflection point. There's a vertical asymptote, but I definitely change concavity there. So I can say with certainty, g is concave up negative 2 to infinity. I did state my, oh, there we go, over here. Concave up from negative 2 to infinity, and g is concave down from negative infinity to negative 2. Well, I've done almost every single possible thing. So I have a graph that's concave up, and you already said I'm going to have, I've got a minimum on the right side, and it's concave up. That makes perfect sense, doesn't it? And on the left side, I'm concave down, and I have a maximum. Okay, that makes perfect sense. So what does the graph look like? Well, there's one more piece of information that I need, and that's going back to here. All right, let me, I'm going to erase this because we've already stated the increasings and decreasings. All right, what about the asymptotes? I have, I'll say vertical asymptote is the line x equals negative 2. If you said an asymptote is a number, that doesn't make any sense. An asymptote isn't a value. An asymptote is a physical thing. It's a vertical line, it's a horizontal line, or it's a diagonal line. So you always express it as a line. So the vertical asymptote is the line x equals negative 2. But as x gets bigger and bigger, this guy here is a transient term. That means my original g, it is correct to say that g of x is asymptotic to what? To 4x. G of x doesn't equal 4x. As x gets bigger and bigger and bigger, g of x is going to think it's 4x. So I have a slant or oblique asymptote, the line y equals 4x. Now this makes for a very interesting graph. Okay. Now I'm going to go ahead and draw the graph on my graphing calculator just to have some fun with you, because it's going to be a little bit on the incomplete side, or so it's going to feel. All right, so let me go ahead and clear this. It doesn't matter what form I do it in actually. So, okay, so y is, I'll do it in that form. It's easier to enter. 4x plus 16 over x plus 2. And let's choose our window. Let's say our window is, I'm going to go -5 to 5, and then I'll do the y window -5 to 5. Okay, great. Now, let me go ahead and graph my graph. All right, so everybody can see my graph. Well, I don't have a graph, because the entire graph is completely outside the window. This is why you don't use preset windows. We're going to come back and change the window, but we don't know what to change it to yet. All right, so you have all the information. You know where it's increasing, you know where it's decreasing, you know where it's concave, up and down. So I'm going to erase all that, because now I want to focus on what the graph looks like and how we know what it looks like. Oops, I just erased important stuff, I know. I'll come back to it. Okay. I do know the following. Okay, I'm going to try to draw sort of an accurate picture. All right. So I know y equals -2, or excuse me, x equals -2 is a vertical asymptote. I know that y equals 4x is a slant asymptote. That means I've partitioned the graph into a region here, a region here, a region here, a region here. Generally speaking, well, first of all, we know we can never cross a vertical asymptote. Generally speaking, you're not going to cross a slant asymptote. You can cross a horizontal, but you're not going to cross these two. So my graph is kind of going to be in regions, but I don't know where. Well, we did say g of 0 and g of, what was the other one? It was -4. Sorry, I erased it. Was -4 our other value?
Yeah.
Okay, we said that g of 0 was a minimum, and we said g of -4 was a max. Okay, what is g of 0? Well, that's easy. G of 0 is 0 plus 16/2. Okay, and it's a blank. We already know it's a minimum. Now, by the way, before we even go on, look at this. As x goes negative without bound, this term is going away. And isn't this just going to get negative huge? Yeah, so this is clearly local. Okay. As x grows without bound, that's going to go up forever. So we already know the max is going to be local. All right, so what's g of -4? That'd be -16 plus -4 plus 2 is -2. 16/2 is -8. So I've got -16 plus -8, which is -24. And we just said, okay, clearly that's a local max. Houston, do we have a problem here? Does anybody see something odd about that statement? Does anybody see anything weird about what I just wrote? My minimum is 8 and my maximum is -24. Does that even make sense? Actually, it makes perfect sense. It does? Yeah, it makes perfect sense. The graph has two sections. That's going to be a local minimum. That's going to be a local maximum. Whoa, that is cool. No, that's not the coolest part. Okay, let me change my window now. Now I'm going to make my window. I don't need to go a whole lot more. I kind of want it centered around -2. So maybe I'll go, I don't know, I'll go maybe 5 units in each direction from -2. Okay, so I'm going to make my X window -7 to +3. I don't really need to go very far. But now I'm going to make my Y window. I need the Y window to go down way more than that. So I'm going to make my Y window maybe -40. And I'll make it go up, I don't know, maybe negative or maybe 25. I don't know. That I might be able to fit everything in now. Okay, now you can see the graphs, but can you see everything you want to see? The vertical asymptote, hopefully you can see. Graphs don't show the vertical asymptote, but it's there because you see the separation. And if you look at the curves, the x equal -2. But now I'm going to make it a much higher y. Okay, so let me change the y window a little bit more, because this is the coolest part of the whole thing. So if I'm going to go a little bit further in the x, maybe x is -20 and x max maybe +20, and now I'm going to make my y min, I don't know, maybe -100, and I'm going to make my y max maybe 75. Let's see if that shows us more. See how the graphs are jetting out? See how the jetting and, sorry, can't say, you see the jetting this way and the jetting this way? Now I've got the scale changed. But what's happening is, as the graph hugs this line, the graph is looking like this line. Now, the line is more diagonal because my X and Y scales aren't the same. But do you see how the graph looks like it's forming a line? Can anybody see that? Not near -2. As I go this way or I go this way, the graph's starting to look like a line. And what line is the graph looking like? Y = 4x. That's your slant asymptote. Now you got to admit, that's kind of cool. Okay, we have one more because identifying asymptotes in a graph is a step that takes place in the first step of the problem. You do the domain and you do the asymptotes before you do anything else. You don't take derivatives to find asymptotes. You just look at the behavior. Now, we know that if I take a limit to infinity, okay, somebody turn out, mute yourselves. There's a lot of background noise. Probably Nate. It's usually Nate. Nate loves us to hear everything that goes on. If I have a quotient of polynomials, for example, that are the same degree, oh, we know how to find that type of asymptote. We've done this before. So consider the following graph. F of x equals x over x squared. Oops, not 2 squared, sorry. This will be the last one we look at today. Okay, I want to know everything there is to know about this graph. And I want to draw a perfect graph, and I don't want to plot any points. Okay, that's the coolest part about calculus. I can draw a perfect graph for the most part without actually using a calculator plotting points if I do all the analysis of the derivatives and second derivatives. That's the key, is analyzing that stuff. Okay, so in this case here, what is the domain? The domain is all real numbers except what? Anybody?
2.
And
-2.
Ah. Now, why is that important? That means, if I write this in a factored form, that means I'm going to have 2 vertical asymptotes. Okay, because there's 2 places x cannot equal, but the y value is fine there. There's no weirdness in the y, only in the x. I'm going to write VA, vertical asymptote, where? At x equal -2 and x equal +2. Now, what is the limit as x goes to infinity of f of x? Can anybody tell me that? What's the limit as x goes to infinity? We haven't done this in a little while.
Is it 0?
It's 0. That means that there's a horizontal asymptote. Ooh, this is an absolute for all functions. If the limit as x goes to plus or minus infinity produces a constant, then y equals that constant is a horizontal asymptote. Because it means as I go in a general that way forever direction, this thing's approaching the x-axis. That's what that statement right there means. I have 3 asymptotes in this problem. Cool. Now, do I have a slant? No. So mark this down. This is extremely important. The only time when you're dealing with rational functions, quotients of polynomials, the only time you have a slant asymptote is when the degree of the numerator is exactly 1 more than the degree of the denominator. Because that means when you do your longer synthetic division, you're going to get a linear term plus remainder. The linear term is your slant asymptote. Y equals the linear term. Because the remainder is going to be a transient term. That's an absolute. My numerator is a smaller degree, so I do not have a slant asymptote. So a simple rule of thumb is I will have a horizontal asymptote anytime the degrees are the same or the numerator is smaller. I have a slant only if the numerator is of degree 1 greater. So you cannot have a slant and a horizontal at the same time. That's not possible. Okay. Now verticals can happen anywhere under the sun. So I've got 3 asymptotes. Cool. So now let's see if we have any critical values or inflection points. So now I need to take derivatives. So f prime of x, straight up quotient rule. So bottom times derivative of top minus top times derivative of bottom over the square of the bottom. So what have I got? I've got x squared minus 4 minus 2x squared. So that's negative. Did I write that correctly? Yes, that's negative x squared minus 4 over x squared minus 4 squared. Kind of ugly, but that's what it is. Now, negative x squared minus 4 off to the side. Negative x squared minus 4. Does this ever equal 0? Well, that would mean that x squared would have to equal -4. And that would give me imaginary solutions. So is my numerator ever going to equal 0? No. So therefore, I have no horizontal tangents. Oh, what a boring graph. Oh, no, it's not boring. But I do have places where I still can change because my denominator is equal 0 in a couple of places. So although this is not equal to 0, and I'll actually state that this is not equal to 0 ever. There is no x value that this ever equals 0. I still want to make my f prime number line, and it's going to have -2 and 2. Now, first of all, notice the denominator, no matter what's in there, I'm squaring it. So the denominator is always positive where it's defined, where it's not, right? It's positive everywhere. So now if I take a hugely negative x, oh, wait a minute, I don't really need to. My denominator is always positive, and tell me about my numerator, -x squared minus 4. Isn't that always negative? So you know what that means? This graph is always going downhill. To and from school, it's downhill. It's all good. This graph is always going downhill. That's kind of crazy if you think about that. I have a graph that is always downhill. But there's a couple of asymptotes in the middle. Interesting. So we're going to say that f is decreasing where? Basically everywhere it's defined. F is decreasing everywhere it's defined. How interesting. Now let's do the second derivative. So at this point, I'm going to write it as a product because my denominator is being raised to a power. It will actually be easier if I do it like this and use product rule. First times derivative of the second plus the second times the derivative of the first. And that looks kind of scary, but if I factor out this term right here, then what I have left is 2x times -2, that's -4x times -x squared minus 4. I have an entire x squared minus 4 times -2x. So that's just a polynomial. That will be a heck of a lot easier to deal with now. So this will be what? 4x cubed plus 16x minus 2x cubed. Did I do that right? Plus 8x. So it looks like my second derivative is 2x cubed plus 24x. There we go. All over x squared minus 4 to the third power. And I can factor that numerator, can't I? That's going to factor as 2x times x squared plus 12 over this. Yikes. But here's what I can say. This will equal 0 when x is 0. Cool. I finally get something here. I'm going to have one place where the second derivative might actually, well, be remotely interesting. So I'm going to erase this stuff because I no longer need it. We did say the function is decreasing everywhere, so I'll leave that up there because we also want to know about the concavity now. So let's do our f double prime number line. So what's going to go on our number line? Well, again, plus or minus 2 and 0. And looking at it in this form. So if I pick a number, extreme negative, it's going to be negative plus extreme negative, that's going to be a positive number cubed. So that's plus. And that would be negative. If I pick a number between -2 and 0, how about -1? All right, -1, this is going to be negative. That's going to be negative. That's going to be positive. So I'm up here now. Pick a number between 0 and 2, like +1. That's still negative. This is now positive. That's positive. So I'm down here. And finally, pick an extremely large number. Okay, this one's going to Gonna do that. So this guy didn't change direction. This changes direction all over the place. So F is concave up. -2 to 0 and 2 to infinity. F is concave down. -infinity to -2, and then again from 0 to 2. All right. Oh, and I have an inflection point, sorry. Inflection point, why? Because I changed concavity here. So when X is 0, Y is also 0? Okay. That's the only point we're going to plot. We're going to draw an absolutely perfect graph, and we're going to plot one point. So how can we do that? Because we have everything in front of us. So let's draw a perfect graph, shall we? This is one of my personal favorites. All right. Usually, if you're indicating a horizontal asymptote, you also put a dotted line where the horizontal is, but our horizontal is the x-axis, so it's often good form. We just do this. That indicates it's that. All right, let's plot our one point. There we go. Now, you guys ready to draw perfection? I am. So here's what we know. By the way, that's the only place this is ever 0. It never crosses the axis anywhere else but here. It's very important to recognize. So let's look what's happening between here and here. Well, let's see. Between -2 and 2, my graph is decreasing. That means it's going downhill. It is concave up from -2 to 0. And it is concave down from 0 to 2. How could that be? Looks like that. That's not horizontal, but that's an inflection point. Okay, so I've just mastered that. That's exactly what it looks like. Decreasing and concave up, decreasing and concave down. We have that right here. Now, how about to the left of this asymptote? Okay, so what's happening from -infinity to -2? This says it's always going downhill. From -infinity to -2, this says it's concave down. It's going downhill and it's concave down, and it doesn't touch the axis. Oops, sorry. I need a little closer. There. Never crosses the axis. It's going downhill and it's concave down. All right, how about the other side? To the right of here, it's decreasing and it's concave up and it never touches the axis. There, we're done. You like that? Yeah, have some fun with this one. So we've got X over X squared minus 4. And now for a window, I want my window to go fairly far in each direction because I want to actually be able to see those. So maybe we'll go, I think it's, yeah, let's just go, well, let's go -10. I'll go the standard -10 to 10. I think that's probably going to be enough. Because I want to be able to see the little in between. Okay. Is it showing up yet? Beautiful. Again, how you make your window sometimes affects how fast it goes. So you've now learned everything there is to know about graphing, and I'm not joking. There is nothing left to show you. So you now know how to deal with the first derivative, with the second derivative, with asymptotes, concavity intervals, increasing, decreasing intervals, finding maxes and mins using first or second derivative test. Life is good. All right. So there's a good stopping point. Some of you guys need your brains to decompress a bit. So let's go.